believable measure of the transverse shear stress. Okay, I'm going to start off by drawing my cross sections and so on, as before. Okay, so I have my neutral axis, neutral fiber, same as before. X-axis, Y-axis, cross-section is the same as before, rectangle. I'm starting off with a rectangle for simplicity, okay, nothing else. The Z-axis is the neutral axis once again. Width of the cross-section is W. And the height of the cross-section, or the thickness, is going to be T and T, so 2T. And this is the centroid. Transverse shear stresses are due to shear forces. Bending stresses are due to bending moments. Normal stresses, average normal stresses are due to axial loads. Okay, so that's typically what we would have been doing a long time back. You will also have shear stresses due to what other aspect of loading? What are the types of loads that cause shear stresses, shear forces? Anything else that causes shear stress? Good person in the laptop open. Anything else that causes shear stress besides a shear force? Torsion. Okay, please close your laptop if you're not doing anything regards to the class here. Alright, so torsion is an example of something that produces shear stresses, but that is going to be different from this. That is why the label is tau transverse. Okay? So I'm going to have shear forces according to the sign convention. The sign convention says that if I look at either one of these shear forces, it's going to take this piece and spin it clockwise. Okay? So this is based on a sign convention, so positive sign convention. And now I'm going to write the formula. We're not going to derive it because it takes at least a couple of lectures to derive it, and I don't think we have the patience. You have to take it as a matter of faith. Okay? So here is the formula for transverse shear stresses. Is V Q multiplied by T, where this T is not the height T. So to distinguish that from what I'm showing as little t there, I'm going to say this is T tau. Okay, so this is not the same as that height T or little 2t that you're saying there. So here V is the shear force. Q is called as the first moment of area. I'm going to show you what it is. INA is the moment of inertia, which is also called as the second moment of the area, which you have seen in statics before, and we are going to refresh our memories once again for different types of cross sections, T sections, L sections, I sections, and so on. Okay, so INA, moment of inertia. About the neutral axis NA, okay, and then this T suffix tau is the thickness at the cross section, and I'm going to talk about what it is, okay. T tau. So I would rather say instead of thickness, the width at the cross section. And I'm going to take a rectangular cross section, try to apply this, obtain a general result, and show you how the shear stresses are different from what we have seen before. I'm I'm going to take off this particular panel here. Okay. So I'm going to draw a cross section and draw the shear force on it. So once again, here is what I'm doing. Taking this, cutting it into two pieces, okay, and I'm looking at the second piece. This is the piece whose cross section I'm drawing. I'm tilting it towards you. This is the y-axis. The z-axis is still the neutral axis. The x-axis is pointed into the page. If I am breaking the beam into this particular way, what is the direction of the shear force on this face here? Can somebody tell me? Yes? It has to be pointed up. Exactly. I'm going to call this S capital. Okay? And what I want to do is I want to employ our formula. So this is T this is T, this is W, and I want to find the transverse shear stress at a point which is a distance y from the neutral axis. Okay? So this is the point which is at a distance y from the neutral axis. I want to find the shear stress at this point. Let's call this as point A. What is tau at A? Okay. So first things first. I'm going to get rid of this guy. I will calculate tau average. What is tau average at any point in the cross section? It is going to be the shear force divided by the area. Okay, so this is going to be just V by A, or this is V by 2 times T times W, because the area is 2 times T times W. Okay, area of the cross section. Okay, does this make sense to everybody? It's very basic stuff, we've seen this before. Okay, now we are refreshing our memory once again. The moment of inertia about the neutral axis for a rectangular cross section is something that I want you to remember. Okay? So for the neutral axis being the direction it is pointing here, moment of inertia I N A, if the neutral axis is Z, then this is going to be 1 by 12 times the base times the height cube. Where my base is W for the rectangle, the height is 2T. You might remember this from statics, or this might have been a distant memory, but we are going to revisit all of these again. Okay? So this is 1 by 12 times W times 2T cube. Then I want to calculate the shear stress based upon the formula rather than calculate it based upon the average stress. So here is what we are going to do. So tau transverse is going to be V as before, no change there. Q, which I haven't calculated, I'm just going to leave it as Q. I'm going to show you how the calculation is performed. This is the one and only time that we're going to see this And the next time onwards, I'm going to go a little faster on this. Okay? Divided by INA is 112 base 2t cube, and t tau, which is the thickness of the cross section or the width of the cross section, is the following. Okay? Draw a line starting from one end of the cross section all the way to the other, parallel to the neutral axis. That line will intersect this point. So here is that line. Okay, so this is a line that is parallel to the neutral axis. It starts from one end of the cross section, goes all the way to the other end of the cross section, and then the total length of this line is going to be t suffix tau. And in our case, that is nothing but the width of the cross section. Okay, so t suffix tau is W for us. Once again, draw a line parallel to the neutral axis. This line is going to start at one end of the cross section. It's going to intersect the points that you have chosen, and it's going to end at the other end of the cross section. The total width of this line is going to be W, t tau. Okay? Yes?
So for all rectangular cross sections, it's going to be W, but then for like a circular cross section,
It will be different. Absolutely.
Okay.
Absolutely. So this will be the same for all rectangular cross sections. Question?
When you first said T transverse, I thought you're like the thickness. I thought you were gonna like the width. I thought it was gonna be like how thick of a cut you took, or like. But
No.
it's not that.
So that's why I said it's the width at the cross section.
Oh,
Right. So I don't want to mistake that with the thickness of the cross section. Okay. So this is going to be the neutral axis moment of inertia multiplied by W. All right. Now we need to find out this Q fellow, and then we are done. Here is how you find Q. Draw the cross section. Okay, so here is the cross section, neutral axis. This is the y-axis, the z-axis is here. I have my chosen point, somewhere here. I drew that line which was intersecting one end of the cross section all the way to the other. This is W. This distance was y from the neutral axis. The total height from the neutral axis to the top or the bottom end is t, little t. And so, this height is going to be t minus y. Does this make sense to everybody? Okay, so this is y, which is the same distance that you've shown here. I have the total width at the cross section, which is drawn starting from one end of the cross section to the other through the point of interest, and that's a line parallel to the neutral axis. And then to find the Q, here is what we do. And I need to clear up this space before I go ahead with my calculations. And at this point, you just have to bear with me. We have to go through with all of these things if we have to start solving problems. I know that your interest is in solving problems for the most part, but we have to go through with all of this. Okay? So bear with me. While we finish this off, there is no derivation. I'm just presenting the formula and I'm telling you how to use the formula. And we're going to exercise this for other cross sections as well. All right. To calculate Q, I take up either the area above this line or below this line. I shade that area completely. And I call that area some A prime. And A prime is going to be the following. It's going to be the width W multiplied by the thickness of that, which is t minus 1. And then, watch this very carefully. This is a rectangle, the shaded area. I'm going to find the center of that rectangle, which is going to be the centroid for that. Okay, so this was my original centroid, which is C. I'm going to call that centroid as C prime. C prime is the centroid of the shaded area, and I'm going to find the distance from C all the way to C prime. Which is a distance that I'm going to call as y bar prime.
Wouldn't that distance be just t minus y over 2? Or not really?
No.
I mean plus y 2.
Yeah, that's what I'm going to say. We have to do all these, right? You can think about it, but we have to do it. Alright, so that's what I'm saying, we have to do it. You may or may not like it, we have to do it. Okay? It might be simple too, but we have to do it. So the total distance is going to be from here all the way to there, which is going to be what? It is going to be the distance y, and then it's going to be from here all the way to the centroid C prime. It's going to be half of this particular thickness. Okay, so y bar prime is going to be y plus t minus y by 2. If I take a common denominator, I'm just going to end up getting t plus y by 2. And q is defined as a product of these two. Is a prime multiplied by y bar prime. So this is similar to taking an area a prime, multiplying it by the distance y bar prime. So what do you do when you take a moment? You take a force, multiply it with the distance. So that's called as a moment. Here what you're doing, instead of a force, you're taking an area, multiplying it by distance, and this is called as the first moment of the area. That's why it's called the first moment of the area. Okay, so if I do the calculations, this is w times t minus y times t plus y, all of it divided by 2. T minus y times t plus y, bear with me for one more minute. T minus y times t plus y is t square minus y square. I'm making use of the formula a plus b times a minus b. So instead of this guy, I'm going to have the following. It's going to be w t square minus y square divided by 2. So this is going to be my q. And what I want to do in the next class before we start solving problems, one more thing, that's just one last thing I have to do, is I want to calculate all of this, crunch all my numbers, compare it with the average shear stress, and you will immediately notice that my transverse shear stress is not a constant at any point. It is now a function of y, and it's a quadratic function of y. It's not a linear stress distribution, or it's not a constant stress distribution. It's a quadratic stress distribution on the cross section. So that is why this is a little more tricky to derive, and so I skipped that derivation in the interests of keeping all of us at bay here. All right? Thank you.